The benefit of logarithmic differentiation is that logarithms have properties that can make things a lot simpler. So, for example, I can expand some logarithms to make my life a little bit easier whenever I deal with logarithms. So, example 14, if I look at this, I'm going to rewrite this as g of x is equal to the natural log of x minus 5 to the 1/3, but because of a logarithmic property, I can pull the 1/3 out in front. So I can rewrite this as g to the x is equal to 1/3 natural log of x minus 5. And now this becomes, taking the derivative becomes much simpler than having to use the chain rule. The chain rule, I would have to do 1 over x and then go from there and then take the derivative of the cube root of x minus 5, which I had to employ because of the chain rule. In this case, I'm going to get 1 over 3 times 1 over x minus 5, and then the chain rule of x minus 5 is just 1. So, okay, this is just going to be 1 over 3 times x minus 5. And you're done. Try the same for b. Pause the video right now. I am hoping this is what you got for B. So along the same idea, let's say we have very complicated problems like in number 15 or in example 15. Again, we have multiplication, we have division, we have chain rule. There's lots and lots of pieces to do this. If I did not do, because I would have to use the chain rule and then all of these pieces inside of here. Oh, there's the product rule with the quotient rule with the chain rule. Oh, there's lots of complicated parts to this. So instead, what we're going to do is we're going to expand the logarithm using logarithmic properties. So then the question is, do you remember those? So remember, in the numerator produces positives. The exponents can be pulled out in front. So the first term, which is x cubed, can be rewritten as 3 natural log of x, then times, so that's a plus once I expand the logarithm. I can pull out the exponent 2 in front, the natural log of x plus 2. And then if it's in the denominator, it's going to be a negative. So, and the power here is 1/2 that I can pull out in front, the natural log of 3x squared plus 9. Now, if you don't remember how to do those, that's something you need to practice. It becomes crucial for this. So we are going to do y prime is equal to, the first term is going to be 3 times 1 over x becomes 3 over x, plus 2 times 1 over x plus 2, x plus 2. Using the chain rule, it would be times 1. Okay, I'm done. Minus 1 over, there's a 2 in the denominator, and then we end up with, so 1 over 2, and then in the denominator we get the 3x squared plus 9. Using the chain rule, it's going to be 6x. Or some people write it directly in the numerator, like so. 6x right there, like that. Oh, look, we can simplify a bit. Now, it depends on the purpose. Sometimes we need to then combine all of these into a single term, depending on the use. If it just says differentiate, essentially we're done right now. If I needed to figure out where the derivative was equal to 0, then I might have to get a common denominator and do that. But the directions here is not saying that. Maybe I should just polish it off a little bit and say, okay, it's 3 over x plus 2 over x plus 2 minus 3x over 3x squared plus 9. I see that I can simplify a little more because the 3 here. So you know what? I'm going to do that instead. It's going to give me an x and then an x squared plus 3, like that. Now I want you to try some of these other ones. Try B. Pause the video right now and try B. In that case, you may want to just separate the numerator and the denominator, make it the cube root of x minus 1 in the numerator and cube root of x plus 1 in the denominator, and then expand. Pause and do it, and come back and check. So like I said in A, right now, A is just if I'm asking you to differentiate, just leave it. But the preferred form often is to have it in a single term because it tells me a lot more. It tells me where the derivative would not be defined and also where the derivative would be zero, if any. So you might have to do a little bit of algebra for some of these. All right, let's look at the next one then. I can do y is equal to the natural log of 1 plus e to the x minus natural log of 1 minus e to the x. And then the derivative is going to be y prime is equal to 1 over 1 plus e to the x. Take the derivative of the interior. The derivative of 1 is 0, but the derivative of e to the x is e to the x minus, and then 1 over 1 minus e to the x. So then the derivative becomes negative e to the x here, or the derivative of the inner function is negative x. Don't forget that. That's actually, I tend to forget this a lot, that negative sign there, but it matters. All right, let's clean it up a little bit. So we get e to the x over 1 plus e to the x plus e to the x over 1 minus e to the x. If that was all we were asking for, then we would just be done. The preferred form, however, most often, preferred form is to have a common denominator. So then I would, in the denominator, have y prime. It's going to leave it a factor. Don't multiply them together. Just leave them as one in the denominator, 1 plus e to the x and 1 minus e to the x. And I need to take e to the x times 1 minus e to the x in the numerator, and then plus e to the x times 1 plus e to the x here. And let's see what that simplifies to. So we end up with e to the x minus e to the 2x plus e to the x plus e to the 2x over 1 plus e to the x times 1 minus e to the x. And then these two fellas cancel out, and I'm left with 2e to the x in the numerator, and then 1 plus e to the x times 1 minus e to the x in the denominator. That would be the preferred form. Now try D. Pause the video and try D. Super messy this one is. So I put it a stop here unless requested to simplify or in the preferred form. I did some of the work out here on the side because it got really messy if I wanted it in that form.